Hi, hopefully you've already watched Molecular Geometry Part 1, and if you haven't, you'll probably want to go back and work on that first. And in this video, we're going to continue on our journey and take a look at examples that have unshared pairs. So, just a quick reminder of the steps that we're going to follow. You're going to start off by drawing out a Lewis structure. We're going to look at the areas around the central atom, figure out how many we have that are bonding areas, and how many unshared pairs. We get the grand total for that, and then we have to figure out the shape. The examples that we'll take a look at in this video all involve unshared pairs of electrons on the central atom, also known as lone pairs. And what you're going to see as a common theme for these is that the geometry of the electron areas is always determined by how many total electron areas are around the central atom. When you try to imagine the shape, you'll be ignoring the lone pairs and just describing the shape of where the atoms are. Our first example that we're going to take a look at is ozone, and that has the formula of O3. The Lewis structure for that is going to have 18 total valence electrons, with oxygen being in group 6, and we have 3 of those. That'll give us the 18 electrons. So let's start to draw out the Lewis structure first. By having 3 atoms that are all oxygen, it doesn't really matter which one you put in the center. We'll just make a little chain like that, and that's going to use up 4 electrons for the 2 bonds that are shown. Now when we start putting the electrons around, we will work on the outside atoms first, and each of those are going to need 6 more electrons to get up to an octet. We had 14 electrons remaining, and now by using up 12 more we have 2 left. I'll put those on the central atom. And then we have the problem that the central atom is only surrounded by 6 valence electrons. So this is where we're going to have to form a double bond. I'm going to erase 2 electrons from the left side, and I'll turn that into a double bond. So I could have also put the double bond on the other side. So this is an example that is going to display resonance that we talked about in some of the earlier videos. And so the actual structure is not going to have a double bond on the left or a double bond on the right. What it really is a blend of the two. And so what we're going to do is we're going to show all the valid Lewis structures, and then the reader should just understand that you have to average all the valid Lewis structures. So I'm going to pause for just a quick second so I can get caught up with that. So here's the other Lewis structure, and now let's start to analyze this using the VSEPR model. Around the central atom, what we can see is that there are 2 bonding areas. I realize that on one of the bonds it happens to be a double bond, but we count bonding areas as just one bonding area, whether it be a single bond, double bond, or a triple bond. So for the oxygen we'll have 2 bonding areas, and it wouldn't matter which one of the Lewis structures you were looking at to analyze that. Also on the central atom we have 1 unshared pair, or lone pair, and so that's going to be right here. And so then the bonding areas were these 2, and the 1 lone pair was right up here. So as a total, that's going to give us 3 total electron areas. As I said before in the introduction, what you're going to do is the overall geometry of what that's going to look like is determined by how many total electron areas you have. And so what you're kind of picturing is the trigonal planar structure, so more along these lines, except when you are considering the shape of this, you don't have to consider where the lone pair is, because that'll just be incorporated into the electron cloud of that central atom. And so visually what that would look like as a molecule is this. And so a good description for that would be to refer to that as a bent. It's like a bent line. Alright, so let's go on to the next example. Our next example is ammonia, but first we're going to erase a few things so I can clear myself some room. Oh, a little bit more here. Our next example is ammonia that has the formula of NH3. we're going to skip right ahead to the Lewis dot diagram, which winds up having nitrogen with 3 bonding areas, 1 lone pair, and then a total of 4 total electron areas around the central atom. Again, we're going to go towards looking at the overall geometry when you have 4 total electron areas around the central atom, and the overall geometry would be that of a tetrahedron. In this particular case, instead of a tetrahedron, what you're going to have then is, without the lone pair being included in the shape, what you have is just a trigonal pyramid as the shape for this one. I'll show you what that looks like so you can picture it easier. Alright, using this model set, the little paddle up at the top there represents a lone pair, and so you can see there's a triangular base and it's a 3-dimensional shape, being that of a trigonal pyramid. Alright, let's do a little house cleaning and then we'll do another example. Our next example is water. So water has a formula of H2O. The Lewis dot diagram puts oxygen in the center, surrounded by 2 hydrogens. And that'll give us 2 bonding areas on the central atom. It'll give us 2 lone pairs on the central atom, and so that's a total of 4 electron areas. So again, with 4 total electron areas, it has the overall tetrahedral shape for just the positioning of the electron areas. But if we're imagining only where the atoms are located, what you have left is something that looks a little bit more like this. It's just a bent line, and so this is another case where the shape is described as a bent. And so there's what this one would look like as a molecule. You can see that I have my 4 total electron areas, the paddles representing the lone pairs, and then the bonds are pretty obvious that you could see there. Alright, let's clean up again. We'll do another example, and we're going to move on to sulfur tetrafluoride. Sulfur tetrafluoride has the formula of SF4, and in our Lewis structure we'll put our sulfur in the center. It's surrounded by our 4 fluorines, each having 6 dots around each. And when you did the Lewis structure, there was 2 extra electrons left over, giving sulfur an expanded octet. So, looking at sulfur, the central atom, we see that there are 4 bonding areas. We see that there's 1 lone pair, and that's a total of 5 electron areas. Alright, so let's take a look at what the shape for this one's going to be. The name for the shape for this one is going to be a seesaw shape. I know it's very hard to visualize what that would look like by looking at my drawing, so let's pop in an image of that so it'll make a little more sense. Alright, here it is. The shape, the seesaw, is based off of the trigonal bipyramid shape, which the trigonal bipyramid is when you have 5 bonding areas around the central atom. And if you look really closely, if you can kind of imagine that teetering back and forth, up and down, you can see how that would actually look like a seesaw. Now, when working with trying to decide where the lone pair is going to go, you can see that here we've kind of done it in this equatorial plane rather than at the top or at the bottom. And that's going to be very important. It turns out that lone pairs, since they are held very closely to that central atom, it's part of the electron cloud of the central atom, they wind up spreading out a little more and taking up more room than would a bonding area that's kind of more stretched between 2 different atoms. With the bonding areas taking up a little bit more room, you can see that with the equatorial plane having bond angles of 120 degrees, it just gives them a little more room to spread out in. We're going to have 2 more examples coming up where you have 5 total areas around the central atom, and then we'll have a couple that have 6 areas around the central atom. So let's erase some of what we have here so we make room. And now let's get on to the next example, which is chlorine trifluoride, or ClF3. This molecule has chlorine in the center. You're attached to the 3 fluorines, and then there winds up being 2 unshared pairs on the central atom. Let's not forget to put in all of our dots around the fluorine. Again, I'm kind of skipping right ahead to the final answer for the Lewis dot diagrams. You would be expected to start these from scratch so that you realize what this shape's going to look like. Looking on the central atom, chlorine has 3 bonding areas. We have 2 lone pairs, and that's 5 total electron areas. As a shape for this one, they refer to this as the T shape. If you turn it on its side, I think you can see where the name comes from. And to try to make it a little more clear, let's pop in an image of what that would look like. Alright, and here it is. So you can see that there are still 5 total electron areas around the central atom, but since we are just describing the shape based upon where all the atoms lie, that one would be described as a T shape. Bond angles for this one are very clear to see. You have 180 degrees if you are going straight across, and you have 90 degrees if you go across and down. Alright, one more example with 5 electron areas. Okay, I've fixed the title. The title before did not reflect that we're doing examples with lone pairs, and that's been adjusted. We're going to be working on our last example that has 5 total electron areas. It's called xenon difluoride. So a little bit of an unusual example in that we have a noble gas involved. So the noble gas is in group 8, so that'll be 8 valence electrons. Fluorine's in group 7. That'll give us 22 electrons total. We'll put the xenon in the center, connected to the 2 fluorines. That uses up 4 electrons, 2 electrons per bond. And now let's work on distributing the 18 electrons. The fluorines will combine together to use 12 of those electrons to get them up to an octet, and then 6 electrons left over. Remember, we have extra electrons, they always go on the central atom. So in this case, xenon gets an expanded octet having 10 electrons around it. So let's tally up and see what this looks like for the VSEPR model. We have 2 bonding areas. We have 3 lone pairs. And that gives us a total of 5 electron areas. Now the shape for that, if we just look at the electron areas, is going to be a trigonal bipyramid. But when you describe the actual shape of the molecule, we only describe the shape of the atoms that are there. And so this one would be linear. And let me show you a model of what that would look like if we use the model kit. And there it is. Alright, now we're going to move on to examples that have 6 electron total areas, and we also have lone pairs involved. Our next example is iodine pentafluoride. That has the formula of IF5. For our Lewis dot diagram, we can see that all of the atoms are in group 7, and with 6 of those, that would be 42 total electrons. Iodine will go in the center, seeing as there is only 1 of those. And let's connect it to the 5 fluorines. Since we've just made 5 bonds, we have used up 10 electrons, leaving us with 32 remaining. Each one of the fluorines will need 6 electrons extra to get up to an octet. So, since we have 5 fluorines, each needing the 6 electrons, that means that we've just used up 30 more electrons, and we have 2 remaining. Now, iodine in the center is already surrounded by 10 valence electrons, but those 2 electrons have to go somewhere, and they're going to go on the central atom. So now as we look at that final Lewis dot diagram, we can see that iodine has 5 bonding areas. We can see that it has 1 lone pair, and that'll give us a total of 6 electron areas. The shape for this is known as a square pyramid. It is based off of the octahedral structure, and let me show you what that looks like as a model. Okay, that leaves us with one last example, and our last example also has a noble gas involved. It's xenon tetrafluoride. Okay, xenon tetrafluoride has a formula of XeF4. We will have 8 valence electrons for the xenon. Fluorine gets 7 valence electrons, but that'll give us 28 for the set of 4. So 36 total valence electrons to work with. For the center, we have xenon, and that is surrounded by our 4 fluorines. Let me just adjust that. It looks like I didn't give myself enough room. So, let's put some electrons around the fluorine. Let me go back. I forgot to take out some electrons for the bonds. We have 4 bonds. That gives us 8 electrons used. 28 electrons left. You can see that I have 4 fluorines, each needing 6 more electrons. So there goes another 24 electrons. And then there are 4 remaining. Xenon already has an octet, but the electrons have to go somewhere, so I put them in the diagram. That'll give us 4 bonding areas, 2 lone pairs, and a total of 6 electron areas. The general structure for that is that of the octahedral, but if you can imagine the octahedral with the top and bottom gone, it turns into a flat structure known as the square planar. Let's take a look at what that model looks like. Here we go. Now you can see that I put the lone pairs opposite of each other. If you remember before when we were doing 5 total electron areas and I started to have some lone pairs involved, we mentioned that the lone pairs take up a little more room, and so if you put the 2 lone pairs off of each other, that'll allow for less electron repulsions, and that's the way that it would have to be done. Alright, well that wraps up all the examples, and let's look at the next page for a summary. This last slide just gives a quick summary of what we've gone over so far in part 1 and part 2 of the videos. Might be a good idea to get a screen capture of this so you can add that to your digital notes.